Let's set up the problem. We have two trains that are 100 miles apart, each traveling at 10 miles an hour. There's a fly on the nose of the first train, who leaves when the trains take off, traveling at 30 miles an hour. When the fly reaches the nose of the second train, he turns around and heads back towards the first. Now this continues until the trains come together and squish the fly. What we want to find is the total traveling distance of that fly. You can model a similar problem using LabPro software. Now this isn't exactly the motion of a fly between two trains, but it is a graph that's rather similar. What this is the vertical distance of a bouncing ball. In order to get this graph, you hold the LabPro motion detector facing the ground and drop a ball underneath it. From there, you can take the maximum points of each arc and find the vertical distance. Using a series, you can then find the total traveling distance of that ball when it's dropped. In our case, the maximum point would be where the fly meets each train. So what we would do is add the vertical distances in our graph to come up with the solution for the total flying distance of the fly.
The first thing we need to do is find how far the fly will travel before it meets with the train. The first time it takes off, it will travel a total of 75 miles. Then, when it turns around, when it meets with the second train, it'll travel 37.5 miles from that point. Turning around again, it'll travel 18.75 miles before it meets with the first train again. Once it gets to the train, it'll turn around and travel 9.375 miles before it meets with the second train. So from here, what we're going to do is take consecutive numbers and make a ratio. So for the first one, 37.5 divided by 75 will give us 1/2. Now we're going to do this with all of these numbers because we want to find kind of like the mean ratio so that we can set up our series, mean being the average. So next we'll take 18.75 and divide it by 37.5, and again that gives us 1/2. Finally, 9.375 over 18.75 gives us 1/2. So we are totally good to go. So we know that our initial traveling distance is 75 miles. And we're going to multiply that by 1/2 to the n power. Because every time our distance is being multiplied by 1/2. We're going to take the sum of this, starting from n equals 0, and going to infinity. There is our sum. Once we have our sum, we can find the limit. So what we'll do is take the limit as n approaches infinity of 75 times 1/2 to the n. Now if we look at this, we can clearly see that it's a geometric series, with z being 1/2. Well, the rule is, for the geometric series, if z is less than 1, the series will converge. In this case, it converges to 150. This means that our fly will travel 150 miles until it gets squished together by both trains. There is, however, a much simpler way to do this problem. Both trains are traveling 10 miles per hour, and they're traveling a total distance of 100 miles. So, we find that they will travel a total of 5 hours, which will put them roughly at the 50-mile mark. If the trains are traveling for 5 hours, so is the fly, because he gets squished when the trains meet. So 5 hours times his constant speed of 30 miles per hour gives us 150 miles of travel.
You can create a calculator program to simulate this same problem. What this program does is it takes in the speed of both trains in miles per hour, so we have 10 miles per hour for each train, It takes in the distance between both trains in miles, so there's 100 miles between our trains, and it takes in the speed of the fly, which is 30 miles per hour. What it returns is the amount of time that the fly will travel and the total distance. So our fly will travel for 5 hours and a total distance of 150 miles. Now this program is pretty simple because it uses the idea that the amount of time that the trains will travel before colliding is the amount of time that the fly will travel. And then it just takes that amount of time and multiplies it by the speed of the fly. Now you can use this to change the speed and the distance between the trains and find how long the fly will travel in different circumstances. The only constraint is that the fly must be traveling faster than both trains, or else the problem won't work.